Okay, and welcome everyone to our first SPCL BCast seminar of the autumn. Thank you all for being here. We're very excited to have Vivek Sarkar here speaking, one of the great people in high performance and parallel computing. He earned his PhD at Stanford University and then was a researcher at IBM Research. He subsequently moved to academia at Rice University, where he was for a number of years. And while there was the E.D. Butcher Chair in Engineering and also chair of the Department of Computer Science. He is now at Georgia Tech, where he is the Stephen Fleming Chair for Telecommunications in the College of Computing and chair of the School of Computer Science. He has done tons of foundational work in high performance and parallel computing, including the JIKES research virtual machine for Java, X10, the broad Habanero and Jalapeno work on parallel computing. He currently leads the Habanero Extreme Scale Software Research Laboratory. And with that, I'll let Vivek take it away. Thank you again.
Yeah, thank you, Nicole. It's a pleasure to be here and to talk to all of you. I know this is being recorded, but I just want to say, don't let that stop you from asking questions in the middle. And I certainly look forward to questions at the end as well. So the topic that I wanted to focus on today is that of automating distributed heterogeneous computing, but from a domain expert perspective. So here's the outline for what I'd like to cover today. And starting with the motivation, when I think about developers in the whole high performance computing ecosystem, I have this visual of an inverted pyramid that I've used for a number of years. And it's not, well, it is drawn to scale, but maybe log scale. So at the very bottom, we have HPC experts, so as they're referred to as ninjas. And, sometimes the new hardware comes out with the programming manual, and that level of programming is only accessible to the HPC experts. Think about using a new FPGA or a new kind of accelerator, or the early days of GPU programming before CUDA came about and libraries were available. The next level in the pyramid, and there are more of such people, are library and framework developers. And here, what we find is there are more of them, but they still need to understand the interface that the ninjas create to be able to develop libraries to map and tune parallel algorithms. But then what I'd like to focus on today are the domain experts. They're interested in solving problems in different domains, and they need ways in which to express new parallel algorithms of future HPC systems. And they'll run into challenges because there may not be libraries available for those and so on. So in this part of it, I'm going to focus a large part of my talk on the Python language, which has been an interesting journey for me and my group to get there. And the main reason, as I'll say in a bit, is it is the dominant programming language and in fact, ecosystem for domain experts who need high performance computing. And certainly this is most visible recently in machine learning and AI applications. So when you look at domain experts, they're faced with this challenge that our entire community is faced with, that Moore's law has ended, and we are entering an era of what we can consider to be extreme heterogeneity. People refer to it as a heterogeneity crisis. So you can see processors proliferating to now things like even near memory processors. Those are the migratory thread architectures. 3D processors, and even looking to a future where quantum architectures can be viewed as yet another but major dimension of heterogeneity, neuromorphic computing, analog computing. There are a lot of these opportunities. At the same time, it's not only what you can do in a system on chip, it's also how you can put it together in distributed parallelism needed for scalability, very much in synergy with the name of your lab at ETH in terms of scalable parallel computing. And so there's an urgent need for new programming systems to enable domain experts to use all this hardware that's now proliferating with the end of Moore's law, new hardware trends. And they're experts in different domains. So I made allusion to the fact earlier that machine learning and AI applications are one where there's a lot of interest from domain experts. And domain experts try to use information from different sources. It's not just about, okay, here's a reference application on our old architecture. How do we move it to a new architecture? They can provide insights related to the data collection, data pre-processing, the use of model selections, model training, how to interpret the results. So there's a lot of co-design opportunity. If you just approach it as a black box, it can be highly inefficient. Another very interesting domain is graph analytics, where, and one reason this is particularly interesting is because applications in this domain tend to run very, very inefficiently on today's supercomputers, usually below 1% efficiency, 0.1%, even the simplest of scalable graph algorithms. And in fact, the graphic that I have over here and the table is from a new program that we have starting up in the US that's sponsored by IARPA. There were some slides presented by the program manager earlier this year at the ISC conference by Bill Harrod. And we also hope to be participating in this program from Georgia Tech. It should be kicked off by next month. Okay, so that's some, another thing that I want to say about motivation is the increasing complexity. So domain experts, they could write Python code that runs on a single CPU. Maybe if they call NumPy libraries, it might use multi-core, or if they call a CuPy library, it could use a GPU, but they basically think in terms of a single CPU. For them to actually parallelize their own code to run on multi-core is a cliff that needs to be scaled. Then you go to the next cliff, which is accelerators, which is not just about identifying parallelism, but also managing data movement, which can be very error-prone or inefficient, depending on how you do it. And then to do something like, getting to extreme heterogeneity with other kinds of accelerators, and finally to clusters, each one is a big cliff. I mean, for example, there have been MPI bindings available for Python for many years now, but they're really not usable. We had a project where we had a domain expert and we suggested that they use that, and then they just chose to instead rewrite all their Python code into C and then use MPI with C, because it just, the MPI paradigm and their approach in Python just weren't working together. So this is also a major issue, that at each level, when you need to scale up your application, it's not a gradual curve, it's like a big cliff to overcome. Okay, so I want to talk about two pieces of work in the time that I have. One is more compiler-oriented, and the other is more runtime-oriented. So the compiler-oriented work relates to optimization and parallelization of Python programs. And I know there's a lot of Python-related work also underway in the SPCL lab at ETH. So when we look at data science applications, there are two sort of current approaches. One is perhaps the mainstream approach in practice, which is you use high performance libraries. So, NumPy, SciPy, CuPy, MATLAB has the parallel computing toolkit and so on. So this is very convenient, and the importance of libraries is really recognized by a community, including the fact that this year's Turing Award winner, Jack Donguera, whose major contribution, which has been game-changing for our entire field of high-performance computing, has been through the role of libraries. So it's an important contribution. But there's still a challenge that, especially if you're exploring new applications, the library APIs may not meet the needs of new applications and new algorithms. Another direction, which has really been spearheaded more by the research community and been adopted in some parts in practice, is the use of domain-specific languages. The idea, so TensorFlow is one example that's definitely used in practice. Halide is another for image processing. But the thing about this is, by design, they're confined to a very, very narrow domain. And that's what gives the compiler toolchain the power to generate very efficient code. And so when you look at an entire workflow or an application that has different kinds of subcomputation, maybe one that needs machine learning, maybe one that needs tensor algebra, maybe one that, who knows, does graph processing. It's very challenging to write an end-to-end application that integrates multiple DSLs. Those tool chains are not usually designed to work together with each other. So we kind of see the work that I'm going to talk about as, rather than a domain-specific language, more like a discipline-aware language. And the idea is that in one language, and Python is a great example of this, you can use idiomatic use of that language to essentially have an embedded DSL without creating separate domain-specific languages. But there were many reasons that we were given when we started this work to not attempt ahead-of-time optimization and parallelization for Python. And this, in fact, I remember Nicole mentioned the Extend project that I had the opportunity to work with colleagues at IBM on nearly 2 decades ago. At that time, another colleague mentioned Python to us, and we said, "Oh, where's the language spec for Python?" And there was a book, and then how a collection like array is defined. Oh, there's a library. It all seemed very ill-defined, and so we said, "No, we're going to use more formally specified languages, I should say, like Java as a basis," and that led to our work on Extend. But over the years, I've realized that we, as people who want to help contribute programming systems, should go to where the programmers are, and they're voting with their fingers on the keyboard. And you can look at GitHub and see that the top 2 languages are JavaScript and Python. And for our HPC applications, Python is very much the preferred language for domain experts. But there were many technical reasons as to why trying to do some heavyweight ahead-of-time compilation might not work. The fact that it's designed for interactive programming, that's got dynamic typing, not to mention that it's multi-threading unfriendly, though there are things in progress to reduce the impact of the global interpreter lock, and so on. But that's exactly why we decided to do it. That's the great thing about being in academic research. If you think something is an important approach and other people say, "Oh, it won't work," well, sometimes that motivates you to push on and say, "Okay, well, why won't it work? And let's see if we can make it work." So we have built this tool chain. It was in a paper that I think I had included a citation before from 2020, the Splash Onward track. In this tool chain, we have this language called Intrepid, which is essentially Python with type annotations in selected functions for function parameters and return value. That's really the primary extension, but I'll summarize the changes in another slide. And we've showed how we can use that as input. Our file extension is pydd for Intrepid. There was a historic reason as to why we have these 2 Ds, because our project was called Daring with 2 Ds. we have a front end, we have static optimization. And the first piece of work I'm going to share, we actually generated C++ code that could be run in two ways. It could be run in what we call the host equal Python mode, where you still have a main Python program and certain functions have been converted to C++, so you can load them as Python C modules and just call them directly. Or if you want to use this really more as a DSL for some, maybe you have some specialized hardware where it's not even feasible to run a Python runtime over there, but it does support C++ code. We have the host equals CPP mode, where the main program and everything is in C++. And these two are, while at a high level, they're similar in content, they're very different in terms of the libraries they use, because when you go through this compilation path, you cannot assume the presence of any Python libraries. So, and you can get some performance benefits just by translating Python style code in Intrepid to C++. But as you'll see in a moment, we get even more significant performance benefits by certain code optimizations that have a much bigger impact on high-level Python code than they might in, say, LLVM. For example, if you have loop invariant code motion, in LLVM, that can be effective. You may take like a single instruction, like an add or multiply outside the loop. In Python, you might be hoisting out of the loop a product of two matrices, because that seems like a single operation. And that's the intermediate code level that we're working on. So in this language subset, which you can view it as having certain functions in your Python program, in the subset here, the data types and statements that we support. The key, I think, burden on the programmer here, but we've since in the second piece of work that I'll mention related to Python, figured out how to get past it. But right now, in this piece of work, we required the programmer to provide types of function parameters and return values for the ones, and then our compiler would infer the other types within the function. So let me give you an idea. So one of the analytics applications in this DARPA, it was a software design hardware program that we were looking at a few years ago, was this word mover distance kernel. And this is how it looks like in Python. And one reason why you can see why Python is so popular with domain experts is you can look at the original algorithm. There's other people's work that was published in Europe 13, and it's Python translation, and it's pretty close to the original algorithm specification, because you have these whole matrix level operations that could be specified exactly as you would when you're writing an algorithm. So for Intrepid, we take the similar approach, but right now, just in full disclosure, in terms of how our software toolchain works, here are the type declarations to say that we have arrays, the element type is float 64, and the rank is 2. So they're matrices in this example. We do have a sparse matrix, and currently it's a little bit of a low-level interface where we have this CSR format, and what is passed as input are really the 3 component arrays needed for CSR. And then we also have this requirement for the programmer to convert those 3 arrays into a sparse matrix. And then from then on, you can use C just like you use any other matrix in Python. And we are working on a future version where we could just, the compiler could generate these additional annotations by just creating a sparse array type. And Julia is also similar. And one thing I'll point out is Julia would also require type declarations similar to what we have. And this is how this kernel would be expressed in Julia. I should also mention, even though what we built looks like an ahead of time and is an ahead of time compiler, You can, in fact, just like actually other compilers, use it from a Jupyter notebook. So here we have a k-means example, and we have this function for update centers, and which we are writing to our PyDD file, and we specified types for the parameters and the return value, and then after we've got that file, we can compile it here in step 15, and then we can import that module opt here in cell 16. And we can define update centers to be the function that we have for the module. Now, this will be our the C++ compiled code. And then when we call k-means, whenever it calls update centers, it'll start calling the one that we compiled. And we've also seen that in terms of ahead of time compilation is relatively quick. I mean, for this code, our translator takes 0.5 seconds, though it is the case then after that compiling the generated C++ code takes much longer, a factor of 10 more. So there is that standard trade-off in ahead of time compilation, but it's not untenable. Okay, so let me very quickly share some results that we obtained using this compiler, and there are more details in the paper. And by the way, I'm happy to leave a copy of my slides also with Nicole. So if anyone would like a copy, please feel free to get it from him. So initially, I'm going to, so here we have a range of benchmarks, including that Synchron one from related to data analytics. And what we're showing on the y-axis is performance improvement over the Python baseline for single core. And the blue bar, there are two other, tool chains that can provide optimized compilation for Python. One is Cython, which has been an early project to translate Python to C. So that's the blue bar. And you can see how, depending on the benchmark, it's sometimes improvement, but in some cases, even a degradation of a factor of between 7 to 8, because it's down to 0.14. Then there's Number, which is a very interesting and robust JIT compiler for Python. And that's the orange bar. It doesn't have any slowdowns really, but it does have variable speed up. And then there's our Intrepid code where we generate C++ and link it in for those functions, just like I showed you in the Intrepid, in the Jupyter notebook example. And those are green bars. You can see here there's a lot of variation. For example, there's one nearly close to 9,000 X performance improvement, and here's 1.5. So the reason for the variation is that it all depends on the extent to which the original Python code used native libraries. In this ISTA benchmark, almost all the time was spent in some NumPy calls, which were implemented in native code. So there was no specific reason to expect that the code that our compiler would generate would be that much faster, but there was still some improvement to get a factor 1.5. On the other hand, in this PR nibble example, it turned out they were doing some computation for which they did not find any Python libraries. So they, so it was all Python code, which runs very slowly. And our code generation made it run nearly 4 orders of magnitude faster. In general, the harmonic mean is a factor of 20 for these benchmarks. We've also shown in the paper how we can get some multi-core scalability. But for this work, we did not do any parallelization for cluster or distribution, which is what I'm going to talk about next. Briefly, we also did a comparison with Julia. This is a little outdated because this dates back to 2020. So we should check again. But we picked 3 examples from the Julia site, Fibonacci, Quicksort, and PySum. And the Synchron example, we translated our Intrepid version to Julia as well. And we looked at the performance improvement relative to Python. For the 3 from the Julia website, both our approach and Julia give significant improvements of 2. And for Quicksort, it's close to a factor of 2 hours, a little more. But for Synchron, we found that Julia did not give a significant improvement. I'm going to tell you a little more about the compiler optimizations. And I've had some discussions with Alan Edelman about this. I think these optimizations could easily be implemented for Julia as well. So the paper has more details, but some of the high-level optimizations that I was alluding to include, and these are done on the Python abstract syntax tree, the loop invariant code motion, which can be applied to array operators. There's a dense and sparse array operator fusion that does a redundancy elimination that you may have seen in other pieces of work, including the TACO project from MIT, where if, for example, if a sparse matrix is going to be multiplied by some dense matrix expression, you want to make sure that in the dense matrix expression, you only compute the elements that will be needed to be multiplied by non-zeros in the sparse matrix. So that's really a redundance that operator fusion removes redundancy for results that would just end up being multiplied by zero. And then there's also the need for some careful memory management, array allocation, and slicing. And what we show over here is that the first column, Intrepid, and this is in the paper too, has the time of just generating C++ code without performing any of these optimization. And then you see the times by adding one of these. And what's interesting is different optimizations contribute more significantly for different benchmarks. So, you can see, for example, loop invariant code motion did not have much of an benefit in Big Clam or Change Point, but it had a significant benefit for ISTA. Likewise, the array optimization had a very significant benefit for SyncOn, going from 47 seconds to 1.225. And the memory optimization also had some significant benefit, like for PR nibble, going from 0.1 second to like effectively 6 milliseconds. So, so these three are very synergistic and work well with each other. So just to summarize, what we demonstrated in this piece of research is that you can create a programming system that takes selected Python functions, generate C++ code, and you can get significant improvement in performance, and and you can even get multi-core scalability. And we talk about some future work over there. Now, the title of my talk talks about distributed heterogeneous computing, and those early results didn't have distributed or heterogeneous. So what we explored after that was, we said, well, how do we get to distributed from Python, and in terms of compiler output? And we decided to target the Ray runtime developed by the Berkeley RISE lab. And because that has a way of distributing code, Python code across multiple processes and multiple nodes. And the other thing we wanted to do was reduce the burden for the domain expert in terms of specifying types. So while they could still specify them, they could be treated as hints, because, and this is something we could have done in the beginning, but we hadn't, because just like you do for optimizing object-oriented programs, you can generate multi-version code. Say, if the predicted type is satisfied, then you have the optimized code, else you have the less optimized code. And the predicted type can be even supplied by the programmer, but the code will be correct even if the actual argument ends up being different from what was supplied. Or you could obtain it from dynamic profiling tools like monkey type and so on. One of the interesting things that we did was, we have a long history of working with polyhedral compilation frameworks in our group, and we were able to extend it to work on this Python code. And it's not just a question of moving to another language, but because Python has these array level operators, they're implicit iterators in the array level language. And for those of you who are familiar with the polyhedral compilation framework, a key foundation is the iteration domain. And so here we were able to combine the explicit loops written by the programmer with the implicit iterations in the array. And then, as I'll show you in a moment, we're able to optimize across those. So yeah, so the big change compared to what I showed earlier is now we're generating Python code as output, but that Python code has annotations to invoke array for parallelism. And I'll say a little more about the application domains later. So just to give you an idea about, in case you haven't come across Ray before, how the compiler might generate code. If you have an input function over here that is reading two files and then adding the reading arrays from two files and then adding up those arrays, or you have a counter class and you're performing increment operations, what you could do using Ray is you could essentially make each read array a remote task, which could be executed in a separate process, either in the same node or a different node. What you get in return are essentially futures. So, when you read array, the two read array calls are initiated asynchronously with ID1, ID2 being futures. And the add also is something that can be done lazily. And it's only when you do a get on the final ID will there be a blocking operation waiting for these computations to be performed. You could also, for shared objects and distributed objects, convert them to actors, and then there can be methods invoked remotely from different processes. So let me talk briefly first about this application, which is the space-time adaptive processing. It's a radar application where they have a need to process data cubes of size 100 by 1000 by 30,000. So that's 3 billion elements. And in this evaluation, we're just going to measure the time for processing 64 data cubes. What we're going to compare is the original NumPy code as a baseline, and then the performance of the code that we generated, taking the original NumPy code as input, but the compiler automatically generating Ray tasks. And another thing that we do as part of this automatic code generation is the compiler has a knowledge base to figure out which iteration patterns can match an existing library call. And if it matches a CuPy call, it gets executed on the GPU, and the compiler also takes care of whatever is needed for data movement for host to device and back. So, but the timings will be for the entire application. Oh, sorry, this was out of order. So I guess since I talked about STAP, I'll get back to this polybench thing later. So just to give you a feel for some of the code transformations that we did, on the left, we have the original NumPy code. And you can see there's just a single loop in line 4 and with two statements in the loop in line 5 and 6. It turns out line 5 in this version has a Namdal's law bottleneck. It needs to be executed sequentially. And there's a 1D statement inside the loop. And there are a bunch of 2D statements after that. Now, what our compiler was able to do was create a unified framework where you had 2D iteration spaces for these statements from 8 to 12. And you had the 1D outer loop and 1D implicit loop for the statement in line 6. And then able to perform some fusion where effectively these statements in lines 8 to 12 got reduced to one-dimensional statements here, starting in line 3, and they were all jammed into the same for loop here, which was originally in line 4. So this fusion is really a result of combining explicit and implicit loops in how we use the polyhedral framework. And I think as many of you are aware, for many of these array processing codes, and in fact, also for machine learning kernels, this operator fusion can be a big source of performance improvement. So with that, these were the results that we got. So the original NumPy code that was written by a colleague who's a domain expert in radar processing took, this is now in throughput, how many data cubes per second. They had a goal in that domain goal of getting to 33 data cubes per second, because if that was feasible, then that's a design they would recommend for whoever's building the radar system. And the original NumPy code was nowhere near the ballpark. It was like 0.002 data cubes per second. The same domain expert did some extra work and separately wrote a CuPy version, and that had a significant performance improvement, but still under 1 data cube per second. Our compiler took the NumPy version as input and automatically generated code, and this was run on the Cori cluster, where you can see using 1 node, 1 GPU node, to up to 24 nodes with 6 GPUs per node, so that's 144 GPUs. And despite that Amdahl law bottleneck, we could still get reasonable scaling and exceed the domain target of 33 cubes per second. So that was really encouraging. And just very briefly on this other one, there's a benchmark suite in the polyhedral community called Polybench. And recently we learned there's a Python version of it. So we tried that out in our compiler, and for about 15 of them. And you can see that we also have the gray bar. Now this is in gigaflop, so bigger is better. The gray bar is the NumPy baseline, and this is on a single node, single GPU. The blue bar is our compiler generating code only for CPUs, and the green bar is also generating CuPy calls for GPUs. And you can see in many cases we have, with the blue and green bar, significant improvements in gigaflops compared to the NumPy version. Okay, so to summarize, in the second part, when we went for distributed and heterogeneous, we went with the approach of type hints and multi-version code generation, and showed how we could extend the polyhedral framework to unify user-written loops and implicit loops in operators, and do automatic code generation for the Ray runtime, and get good performance results. Okay, so now in the time that I have, I'm going to switch gears a little and go from compiler to some runtime, recent runtime work in our group. I just want to first recap the bulk synchronous parallel model that all of you certainly in the SPCL lab would be familiar with. It's served our community, our HPC community really well for many decades. And in this pure form of the model, you have a series of these phases or super steps, where in one super step, each PE does some local computation, initiates some communication, and then you have a barrier synchronization, after which you're guaranteed that all the communications that were initiated have completed, and then the next super step can start. What we've recognized the need for is something that we call fine-grained asynchronous bulk synchronous, that during a super step, we should be able to allow offloaded active messages. And this is going, as you'll see in a moment, inspired by the actor model. So the idea is, for example, PE2 can send a message to PE0, and the runtime system at PE0 will figure out at some point in time to perform, you can think of it as an event handler or message handler, for the code to be that results from the message on PE0. And as part of the event handler could result in generating a new message that in this case goes to PE1, but they're asynchronous. So when there's no interrupt over here, there's certain, as in a cooperative scheduler, certain points where the runtime will check to see if there's some messages that need to be executed, and otherwise continue with the local main program with the PE code. And when you have this extension, one key requirement is that this barrier also needs to be extended, because not only is it waiting for all the local computation in the blue to complete, but it also needs to make sure that all messages, these asynchronous messages that were initiated and that might be in flight, they've reached their destination and the message handler has also been invoked before you get past the barrier. We found that this is particularly useful for graph algorithms where you can have a lot of this local work in sort of one time step, and then you reach a barrier, and then you can continue to the next time step or super step or phase. So to realize this model, as I mentioned earlier, we've extended the actor model with basically for scalability with multiple mailboxes, with symmetric mailboxes, just like you launch an HPC program on, say, let's say 10,000 PEs, you get 10,000 instances of the same actor. And we also have this automatic termination detection for messages, which is a big boon. If anyone's programmed with the actor model, you know that any kind of coordination or consensus is very challenging to manage yourself. You have to maybe keep track of counters and exchange messages to make sure that all the PEs have completed their work. We take care of that in the runtime. Another very, very important thing that we do in our runtime is message aggregation automatically. So in many algorithms, particularly graph algorithms, the logical message can be very small. It could just be 8 bytes. But we all know that's literally sending an 8-byte message at a time over an HPC interconnect is going to be highly inefficient. So we have this runtime layer, and that's built on some other work that's been done in the past by others called conveyors, where we do this message aggregation automatically. And then finally, we need this asynchronous tasking runtime that can switch between the main PE code and the handling of active messages that it receives. And we've got this tasking runtime that we call the Habanero C library, HClib, and that was adaptive for this purpose. Just very briefly, one of the reasons the actor model has been, adopted and pursued for so many years is very elegant. It's a concurrency model based on asynchronous messaging. And I would just say, as we move towards hardware in the post-Moore's law era, I think asynchronous communication is inevitable because you're talking about heterogeneous hardware with different clocks, different domains, physical domains. Thinking of some synchronized way of coordinating across all of those heterogeneous domains is completely impractical. So that's one advantage of the actor model. And in general, this has not been explored much in the HPC community, though Charm++ is definitely one exception in that regard. So what we've done is we've actually extended an actor with multiple mailboxes. Each mailbox has its own message handler, and they're symmetric, means that when you launch an HPC program, you get one of these per PE or rank, as you might one actor instance. And as I mentioned earlier, we have this automatic termination detection. The paper has details, but I'm going to give results for some mini apps from this benchmark suite called Bail. They are very simple examples, as you can see, but there's a belief by many domain experts that if you have a runtime that can do these examples well, then there's a good chance that that runtime will work well for the larger irregular applications. So just to give you a flavor of what I'm talking about, here's a very simple example. It's called index gather. And the idea over here, this is what's called the UPC version, which is synchronous but highly inefficient, as you'll see in a bit, where index and gather are local arrays, but data is like a distributed array across multiple PEs. And what each PE is running this code in SPMD fashion, and is collecting data based on this indirect index. And so that means this could end up being remote reads from remote PEs, and usually is most of the time. So a typical processor will then block for each such read when doing this version. But certainly the code is easy to understand. The conveyors version, this is the library I mentioned earlier. This is one that's accessible to Ninja programmers. It has APIs like convey begin, convey advance, convey push, convey pull. Each of these can return false if they fail, and it's really important to handle the failure mode. And there's this intricate thing going on with two conveyors where the code for sending out the requests for data and processing requests received are kind of interleaved. So people who are able to write this code do get good performance, but it can be very challenging to write that code in terms of the expertise needed. On the other hand, our actor, or as we call the selector version, shown on the right. So here what we do is each PE is, like the original version, well, it's figuring out the location. This should be a high-level call. It's right now, it's the cyclic distribution as hardwired with the mod and div operations. But the active message part is sending to the destination PE a request, which is specified by a C++ lambda. And the body of the request is to load the data, which would be a local load because it's going to be executed on the destination PE where the data element resides, this read of the data subindex sub I. And then as part of the message handler, there's another response message, asynchronous, that is sent. And the lambda there says that when that message reaches the destination, which was the originator of the original message, you do the gather store. That's what the get target is. Basically, it's storing in the gather array. So I hope you get the idea from this. And as I alluded to earlier, we have a runtime implementation based on our HC library. It needs to, under the covers, so that we don't burden the programmer with this, it needs to have these communication tasks, which, depending on your communication runtime, it may be event-driven, it may be polling-based, which keeps track of when aggregated message buffers need to be pushed out, or when something has been received and buffered and is ready for processing. The programmer is completely unaware of the aggregation that's going on. Like the code I showed you earlier, each send is just an 8-byte value. So really quickly, some evaluations. This was also done on Cori, which has a Cray Aries interconnect. And we go up to 2 KPEs with 64 nodes. It's all CPUs, no GPUs being used for this. And each PE is multiplexing the original computation task, like the blue bars I showed earlier, and the communication task, the red bars. And I'm going to compare 4 variants. One is the UPC version, which is very easy to write, but can incur a lot of inefficiencies. I think for 2 reasons. One is because they're blocking reads, and second is they're fine-grained reads. So you're doing like 8 bytes at a time. There's an OpenSHMEM version that does the same thing directly using OpenSHMEM lib getput APIs. There's a conveyor version, which is the Ninja level code that I showed you earlier, where the programmer has to take care of handling all these error cases. And then there's our selector code, which uses this actor model in general with C++ lambdas. So I'm just going to show you for the 7 Bale benchmarks what the performance looks like. This is execution time, so smaller is better. The blue bar is UPC, the orange bar is SHMEM, and conveyor and selector, which is our selectors, our work, come to the end. And you can see over here, oh, and I should mention this weak scaling. So with perfect efficiency, it should be the same time as you increase the number of PEs. So you can see the conveyor version is pretty close. It only goes from 0.5 to 0.6. Ours goes from 0.5 to 0.7. The UPC version, on the other hand, goes up to 44 seconds. So, we are talking about a speed up of, nearly 80 or 90 over here for this example. If you look at index gather, the code I showed you earlier, again, you can see some significant speed ups. With the fact is that our actor selector version is pretty comparable to the conveyor version. And here there's a fact of maybe 15 or so relative to the Schmem version. There's something called permute matrix. Here, the factor improvement is more than a factor of 20. But again, the selector version is close to the conveyor version. Random perm is another, also more than a factor of 20. Topological sort is more about a factor of 10. Triangle counting, something you may have come across as part of graph analytics. Here, the factors, almost that of 45, depending on which version you're comparing with UPC or Schmem. And, there are cases when the selector version is a little slower than the conveyor version, but relative to the magnitude of the other approaches, it comes very close to the conveyor version, while making it, we believe, much easier to program than the conveyor version. Okay, let me wrap up now. So I gave you like two examples, one related to compiler optimizations of Python code where we generated C++ in one case, and in another case, we generated array runtime calls. And then in the second part, I talked about runtime. But in general, in our lab, we are very interested in research related to parallel programming models, compiling for parallelism, parallel runtime systems, and also debugging and verification tools, such as data race detection, deadlock detection, and so on. So obviously, I didn't have time to talk about all those other topics. I've mentioned some relevant references for work in those four categories. It may sound like a really broad scope, with programming model, compiler, runtime, and debugging work. But actually, I believe for our lab, it's quite integrated because we have a common, what we call this Habanero execution model that all the pieces of work use as a foundation. And that's based on these lightweight asynchronous tasks, some of which the ideas were influenced by the original extend work I did when I was at IBM. And this notion of locality control and computation and data distributions and various mechanisms that we worked on over the years for inter-task synchronization. And, we've had the opportunity to work on different language extensions for OpenMP, Python. We're working with the Chapel team, language extensions of C, C++, and we've even experimented with some this actor model actually with JavaScript and with Rust and so on. Compiler, I mentioned the polyhedral work we're doing, but we also do quite a bit of compiler work in LLVM. And in the past, we've done bytecode optimizers for Java. And the runtime, we have these various runtime systems we work with and the debugging tools that I mentioned earlier. But usually if a student is working, let's say on a compiler part and someone else is working on the debugging part, they can still interact with each other because they all go back to the same execution model. Oh, just a couple of group photos of us, our group and some other groups doing an outing in Atlanta. And during the pandemic, this was taken in 2020, I think. Here's a group photo where we felt comfortable meeting outdoors. And I brought a bag of cookies along. And here are members of the group. And I would encourage you to visit our website, email me if you're interested in learning more about what we are doing or collaborating with us. We would really like to learn more about related work that you might be engaged in. And with that, I'd like to conclude that, today's focus on Python provides a path for what many people have mentioned as a holy grail, which is abstraction without apology. The idea is the domain expert specifies the application algorithm very declaratively. The programming model can provide robust semantic guarantees so as to ensure that you don't run into complicated issues with data races, deadlock, memory inconsistency across accelerators, those kinds of things. The compiler can generate multi-version code for different inputs, different target devices. We've already been doing that for CPU and GPU. And the runtime then schedules the code and data movement on a distributed heterogeneous HPC platform. So I think these are exciting times because there's new parallel hardware with the end of Moore's law. There are new applications that are interested in HPC, certainly AI and machine learning, but also graph analytics, data science. There's some real-time processing, even embedded. There are new languages, Python, of course, but Rust is an interesting possibility, many domain-specific languages to explore. And I think with these changes, we can completely reimagine what the software stack should look like for high-performance computing. And I'm always interested in learning about new directions that others might be working on. So with that, let me stop and welcome any questions.
Okay, thank you, Vivek, for the great talk. I learned a lot. Before we move to questions, I just want to mention that this is the first of what we plan to be a number of BCast talks this year. We're finalizing our schedule soon, so please do check our website for future talks.